I'm a mathematician, actually. I'm the only mathematician in this group, so I'm the boring one. And that's why they scheduled me right after lunch. So, you can have a nice nap. And it's good for you. Math is good for your digestion. So, but I want to talk about mathematics and how it connects to the physical reality. And what is mathematics really about? So, I want to start with this great quote from Galileo. The laws of nature are written in the language of mathematics. And without mathematics, he says, we are left wandering about in a dark labyrinth. So mathematics has been, for centuries, instrumental in the progress we have achieved in science and technology. And in fact, some people have said even that the effectiveness of mathematics in natural sciences is almost unreasonable. Eugene Wigner, Nobel Prize winner, has said that. So that brings up a very interesting question as to what is math? Is it something that we find in nature? Is it something that we create? Why is it so effective in the physical reality? In other words, does math exist by itself without physics? And that's a very interesting question because, of course, there's so many concepts, so many mathematical concepts we come across in our experience in a world around us. I mean, we count 1, 2, 3, 4, 5. That's how we get acquainted with the concept of numbers, which, of course, is very important. We see various geometric shapes around us. But actually, for someone who's a practitioner who does mathematics for a living, you start seeing things, you start seeing parts of mathematics which do not manifest themselves immediately in any obvious way in the world around us. So I would say that, in fact, it's really kind of, he hit the nail, the Wigner, when he said that, because these important discoveries in physics have been preceded by works in mathematics, but those works were done oftentimes without any reference to physics. They were done within the narrative of the subject itself. Robert Dijkgraaf talked about Einstein's relativity theory being preceded and anticipated almost by a work of a mathematician, Bernard Riemann, 60 years earlier. So Riemann talked about geometric shapes and the intrinsic structures of geometric shapes, like a sphere or a surface of a donut, without referring to a landscape, an ambient space into which they're embedded. And people were saying, why are you doing this? Don't you know that every geometric shape we encounter in the physical world around us, every curved shape, is actually embedded in a flat three-dimensional Euclidean space? Because that's how we humans have thought about the world around us for millennia. It is flat and Euclidean. You can draw three, axes, perpendicular axes, to create this Cartesian coordinate system. And then Einstein showed that that's not the case, as we have heard already several times in these proceedings. So, in other words, that theory, to even talk about a space which is not flat, which is curved, we need a mathematical theory, because we cannot even imagine how can it exist by itself. Well, where is it embedded? Well, it's not embedded anywhere. It can exist by itself. But for that, you need this mathematical theory. So that's what I mean when I say that that discoveries in physics were preceded by works in mathematics. And so this is a very interesting, very interesting element. So then, of course, my main point then is that mathematics is almost kind of like this hidden parallel universe of elegance and beauty, which is intricately intertwined with our world. And today I want to talk about some aspects of this world of mathematics and the subtle connections between this world and the physical world, the physical reality, which we all see and love and observe. And what I really want to talk about today is this idea of unification in mathematics. In the previous lectures today, you have heard about the idea of unification in physics, where roughly you would want to have a t-shirt which would have all the equations describing all of physics written on maybe on the front and the back. Maybe it would not be enough to just on one side, but maybe on both sides. So this idea has driven so many scientists, so many physicists for many years. But actually in mathematics, it's very similar. In mathematics, we also have this yearning almost, or this desire to understand things from very few basic fundamental principles. And to find connections, find invisible connections between different parts of mathematics, which at first glance seem to be light years away. So I really want to think of mathematics as this giant jigsaw puzzle. Except you don't know, they gave you the pieces, but they didn't give you the box. So you don't know what the final image is going to look like. And you're trying to assemble that image from those pieces that you're given. And so different parts of mathematics then would be different parts of the puzzle. When you try to solve a jigsaw puzzle, maybe if you do it with your friends, maybe it's a big one, so you work on one part with some of them, then others working some other part, But eventually you would like to connect these parts. And another analogy is like continents. It's like different continents that we have. So let's say one subject would be like North America and another one would be like Europe, and you're trying to find links and connections between them. So what are these different continents of math? What am I talking about more specifically? So there's number theory. The fans of Matrix will recognize this image. There's number theory. We'll talk more about numbers. What kind of numbers are there? And what are they good for? That's one subject, which has a long, long history, right? Then you got harmonic analysis. Harmonic analysis is best understood, I think, is in terms of as when you study sound, when you appreciate the sound of a symphony, we'll realize that the sound of a symphony, this beautiful, sophisticated sound, is actually made from different notes on different instruments. So it is, as a mathematician would say, is a superposition, or it's a kind of a composition of different pieces, of different sounds of different instruments. And each of those sounds is represented by a wave, or what we call a harmonic, a simple harmonic. And the frequencies of those waves are multiples of each other. And the idea is that when you superimpose them, when you hear different instruments, that creates this beautiful symphony. Okay, so that's the idea of harmonic analysis. And again, we'll talk more about this in a few minutes. Or another subject, geometry. So this is an example, behind me is an example of what we call in mathematics Riemann surfaces. It's the same Riemann, the same mathematician Bernhard Riemann, German mathematician Bernhard Riemann, who came up with the ideas of Riemannian geometry, so fundamental to Einstein's general relativity theory. He also developed the theory of two-dimensional shapes, like this one, or think of the surface of a sphere, surface of a basketball, say. We'll return to that later. Those are the what we call Riemann surfaces. So you see here, I give you examples of three different areas of mathematics, three different continents, if you will, of that giant jigsaw puzzle: number theory, harmonic analysis, and geometry. They all look very different. They are driven by different kinds of problems. They are developed by different people to different ends. Could it be that they are somehow secretly connected? That there is some story behind this, which actually brings them all together? Well, it turns out there might be. And that's what I would call a kind of a unified theory of mathematics. That theory, in fact, was initiated about 45 years ago, in the late 60s, and it is now called the Langlands program. I really like to think of it as a kind of a grand unified theory of mathematics. Not in the sense that it necessarily unifies all of mathematics, but it unifies many different parts, and hopefully, and it has been, historically, has been sort of propagating to more and more different domains, different fields, and so maybe eventually other fields will be affected as well. And but the essential part is that it does connect these different continents of mathematics. Robert Langlands, the mathematician who initially initiated this theory, who started developing these ideas, Robert Langlands, Canadian-born mathematician who's a professor at the Institute for Advanced Study. Here he is at his office, which incidentally is the office formerly held by Albert Einstein. So I always kind of, as a half joke, I always say, everybody knows about Einstein and his theory, but very few people know about Langlands and the Langlands program, which I think one could argue is just as fundamental to humanity as Einstein's general relativity theory or his works on relativity theory and other works, which is a very nice office, by the way. So as Robert Dijkgraaf can attest, I have collaborated with Langlands, so I've been there. Just a little name dropping. I want to tell you about the Langlands program, and I want to tell you how it connects these different continents of mathematics. And the first thing that you need to know is that the key concept which permeates all of this, seemingly esoteric and abstract domains of mathematics is the idea of symmetry, something that we experience in our lives, in our daily lives, really, on a regular basis. If I say the word symmetry, what images are invoked? We think of a snowflake, we think of a butterfly. We maybe think about the human body, here represented by the beautiful drawing of Leonardo da Vinci, the Vitruvian Man. But what is it? What unifies all of them? What does symmetry really mean? So let me explain it by using sort of very mundane example. Round and square glasses. I actually don't have round and square glasses, but I have a round and a square bottle. So I will use this as my models. So the point I'd like to make is the following. That I want to ask the question, which one is more symmetrical? And you don't have to answer right away. And it could be different answers, I suppose, in different contexts. But in the context which I'm going to explain, the answer is clear. But we have to understand what does it mean to be symmetrical. If you're a mathematician, you don't take anything for granted. That's sort of like a definition, almost a definition of being a mathematician. Or scientist in general, I suppose. So what is a symmetry? What does it mean? What do we mean when we say that something is symmetrical? Well, in mathematics, we approach it in the following way. Let's say I have this round bottle. I can rotate it by any angle around its, the central axis, and it will stay the same. In other words, if you look away for a second, and in the meantime I rotate it, and you look back, you won't know the difference. Well, let's ignore that there is a labeling and so on. Let's just think of it as a truly round object. But if I have a square bottle, that wouldn't be true, right? If I rotate it by a random angle, you will know the difference. It would shift its position. It's only if I rotate by 90 degrees or 180 or 270 that it will stay the same. So these transformations, which preserve the object, its position and shape, are called symmetries. And we have just seen that the round bottle has infinitely many symmetries. Any rotation will do, any rotation by any angle at all, 30 degrees, 50 degrees, 35 degrees, whatever you want. Whereas for the square one, only 4 rotations are allowed. Only 4 rotations are symmetries. That's why we would say that the round bottle is more symmetrical, right? That's the first observation. But now we can go further and we say, okay, what are those symmetries? Let's actually kind of behold those symmetries as points of a new abstract object. So what are the symmetries? The symmetries are, for a round table, are just all possible rotations, right? Every point on the circle represents an angle, a particular angle. I have to fix one point and to declare it to be rotation by 0. And then every other point would give me a rotation, another rotation. For example, that point is a rotation by 30 degrees, and then I can easily mark any other rotation as a point on that circle, right? So the circle, the totality of the points of the circle represents the totality of all symmetries of a round bottle, or a round glass, or a round column, any round object. In fact, being round means to have the circle as the set of its symmetries. And likewise, for the square one, there are only 4 elements. Rotation by 90, 180, 270, 360 degrees, right? And so we have arrived at a very important concept in mathematics, which is called the concept of a group of symmetries. And you may have seen this before, but usually in mathematics textbooks, they explain this by some axioms. They say a group is a set with some operation which satisfies such and such axioms. It's very hard to understand this. I remember when I was first learning this stuff, it's very difficult. It's like, what? I have to memorize this now? But actually, the idea is very simple. You just have to think about transformations which preserve the object. But think of them as points of a separate abstract object which does not exist in physical reality the way the bottle or the glass exists. It's something that we behold sort of in our consciousness, in our mind. But it's just as real. This mathematical object is just as real. And every point on that object has a concrete interpretation as a particular rotation of that glass or that bottle, right? And so the circle is a group, and this collection of 4 rotations is a group. But what does it mean? So what can we do with this now? Now that we see that the circle, kind of this abstract circle, has responsibility for all the rotations, what can we do with it? Well, we can apply rotations back to back. We can apply symmetries back to back. Okay? So I rotate the glass by 30 degrees, then I rotate it by 20 degrees more. The result is a rotation by 50 degrees. So I can apply rotations back to back, or general symmetries in general. And this is the operation. This is something we can do with points of the circle, which we cannot do with points of the bottle, right? So it's sort of, there's slightly potential for confusion here because the circle looks kind of like the bottle itself, but it isn't. The points of a circle are not points of the bottle. They are, each point is a rotation. It's a transformation. And transformations can be applied back to back. And that is the main idea, that it gives a certain, the circle comes alive. It has its own life. A very rich, fulfilling life, that every 2 rotations give rise to a third one. And that structure satisfies certain special properties. The example is a little confusing because, like I said, circle is kind of, we look at the circle, it's almost as if we are looking at the bottle from the top. So to make it less confusing, let's look at the next example, which would be rotations of a sphere. You see, in the case of a sphere, there is more. Think of a sphere as a globe, as a surface of the Earth, which is very close to being spherical. Okay? So then, what kind of transformations would preserve its shape and position? Well, we can rotate it around the axis connecting the North Pole and the South Pole, right? So again, we get a rotation, and by any angle. But these are not all possible rotations of the Earth because we can choose a different axis of rotation. It doesn't have to go north to south. Maybe it's better to think of a basketball. Think of a basketball. Put a basketball on the floor. Where it touches the floor, we'll declare it the south pole of the basketball. And then the point on top we'll call the north pole. And we'll rotate it around that axis. But then if I put it differently, I will get a different axis. Or visualize it as kind of a slanted axis going through the center of the basketball. And then you can rotate around that. So you see now there are many more possibilities. First, you have to choose the axis of rotation. And second, you have to choose the angle of rotation. So there are many more choices. So you get a group which is called SO3. Robert Dijkgraaf talked about groups. He talked about the groups, the gauge groups, which appear in a standard model, for example. He talked about U1 and SU2 and SU3. He even talked about SO10, which, by the way, SO10 is a close cousin of SO3. SO3 is a group of rotations of the sphere in the 3-dimensional space. SO10, which appears in one of the GUT, Grand Unified Theories of Quantum Physics, is a group of rotations of a sphere, hypersphere, if you will, in a 10-dimensional space. You see, so that's where these names come from. SO stands for special orthogonal. Okay, so we get these groups, and the circle is the simplest one. Rotations of a sphere is the next one. But here's maybe a little bit more playful. Rubik's Cube, by the way, they celebrated, I think, 40 years recently of the invention of Rubik's Cube. And that's kids love this example. Which, by the way, people ask me, what kind of math should we teach, which we don't teach to kids these days? And I say, well, we have to teach symmetries and symmetry groups. And the best way to introduce symmetry groups to children is through the Rubik's Cube. I recently went to a school in Manhattan, 4th, 5th, and 6th grades, and I talked to them about groups, and I brought a Rubik's Cube, and I wanted to learn how to solve it, but I couldn't. But when I came, so I tried 2 by 2 also. And still was hard, but I was able to solve 1 by 1. So anyway, but half of the kids in the classroom actually knew how to solve it. So, and then when I explained to them that, when you're solving this puzzle, you're actually discerning the structure of the group of symmetries of the Rubik's Cube. Because each rotation that you use in the Rubik's Cube is one of those transformations I talked about earlier, which preserve it. right? It doesn't preserve the colors, but it preserves the position of the cube. It changes the colors. And so the winning strategy is a particular way of finding sort of the right path of elements of that group. So this, up until now, was a discussion of symmetries in geometry, because all of these are geometrical objects, bottles, glasses, things like that. But symmetries are also paramount in quantum physics, and we have already seen examples of that in Robert's talk, right? We talked about quarks, elementary particles, and how the classification of those particles was achieved by using this theory of symmetry. So let me just recap quickly. So of course we know that there are many elementary particles. For example, the nucleus of an atom, of every atom, consists of protons and neutrons, and for a long time physicists believed that those were indivisible elementary particles. And then came as a surprise, which was that actually they had trapped inside, were each proton and neutron had 3 smaller particles called quarks. But how did physicists come up with this idea? Well, in the 1960s, by 1960s, physicists discovered this proliferation of elementary particles. They kept discovering more and more particles, which made one of the physicists, Robert already mentioned that quip, who ordered them. And the great physicist Wolfgang Pauli joked that physics was turning into botany because you have all these particles. What does it all mean? So physicists needed a theory to explain this maddening proliferation of those particles. And the answer came at first as a classification scheme, which used group theory. And so this classification scheme, which gave the answer, which was that a proton and neutron, each of them has 3 quarks trapped inside, up and down. One of them has 2 downs, 1 up, one has 2 ups and 1 down. But initially, the idea was his idea, Gell-Mann's idea, and also Yuval Ne'eman independently, was the idea that you kind of group this. Well, no pun intended, because the word group, of course, is used now in a specific mathematical sense, but kind of put these particles in families of 8 and 10. And Gell-Mann called this eightfold way, referring to the noble eightfold path of Buddha. And so the idea was that you can organize them, elementary particles, in this kind of patterns, and within each of those groups, each of those sets of 8 and 10, octuplets and decuplets, they would have sort of similar properties. So here you see, for example, neutron and proton at the top of the picture. But then he realized that actually the reason why you could do that, what was behind this classification, was a symmetry group. And that symmetry group is called SU3, and which, by the way, is the same name as the SU3 which Robert mentioned in the context of gauge theory. But it's a different SU, to make things a little more confusing, it's a different SU3. It's a global, so to speak, it's a flavor SU3, as physicists call it, not the gauge SU3. Which, by the way, SU3, we talked about SO3, special orthogonal group. That's the group responsible for rotations of a 3-dimensional Euclidean space, or rotation of a sphere in the 3-dimensional Euclidean space. SU3 is almost like this, except you replace real numbers by complex numbers. I mean, it's maybe easier said than done, but imagine that, your Cartesian space, Cartesian coordinate system, you have 3 axes, right? X, Y, Z, and along each you have real numbers. Now imagine that each of those is replaced by complex numbers. And complex number is like a pair of real numbers, because it has a real part and imaginary part. So you get in total kind of a 6-dimensional space, right? And so then the cousin of the group of rotations in the Euclidean space will become this group SU3. That's where the name of the group came from. Special unitary group. Unitary is the analog of orthogonal in the case of complex spaces. And I like to tell the story because, this is how I came to mathematics, actually, through this group SU3. Because when I was growing up, I hated math, like most people, I not hated maybe, but I wasn't particularly fond of it. I thought it was the most irrelevant and boring and lifeless subject. But that's because I didn't know what mathematics was really about. I only knew what they were teaching us at school. But I was lucky because I was very curious about elementary particles and quantum physics. I wanted to be a quantum physicist. And then, when I was in the last year of high school, I met a mathematician who showed me what mathematics was really about. And the way he showed me was because he knew I had an interest in elementary particles. He said, well, have you heard about quarks? And I said, yes. But do you know how physicists were able to theorize quarks? How did they understand? Because really it was an absolutely revolutionary idea to say that there is particles which no one has ever seen. And on top of that, they have fractional, their charges are fractions of the charge of an electron, 1/3 or 2/3. Crazy, right? So how did physicists come up? And he said, well, do you know about this? And I said, well, yeah, I read about in the books. I saw diagrams, like the diagram I showed you before. I saw the diagrams, but I didn't know what the theory behind it. He pulled a book from a shelf and he opened it. And I saw the same diagrams, but now they were not just some diagrams without any explanation. There was a coherent story. I couldn't understand it at the time, but I could see that it was there. And that's how I knew that I wanted to know it, to understand. And he said, well, you have to understand the group SU3. So for me, sort of SU3 is sort of rhymes with mathematics. And of course, we need large and expensive and sophisticated machines to make progress in science. And we have heard today about the great experiments that physicists, really brave physicists, really do in advancing the frontiers of knowledge. But sometimes very important discoveries are also made on the back of an envelope by using seemingly esoteric and abstract mathematical theories such as group theory. So this mathematical concept really was instrumental and still is. You think about Higgs boson, of course, which was in the news lately, and Higgs boson is a particle which is also connected to symmetry, which is involved in a mechanism for breaking the symmetry. So sometimes symmetry also needs to be broken, but in a controlled way, also by using a sophisticated mathematical theory. So that's where it comes from. So which brings me to this beautiful quote from Richard Feynman, who said that people who wish to analyze nature without using mathematics must settle for a reduced understanding. And I think we should not settle for a reduced understanding. We should gain as much understanding as we can. Now I want to talk to you about how this idea of symmetry, circling back to the idea of unification in mathematics. I said earlier, continents of mathematics, number theory, harmonic analysis, geometry. A Langlands program that unites them. Langlands program in which one of the main ideas, main concepts, which permeates Langlands program is the concept of symmetry. But so far, I have only shown you how symmetry plays out in geometry, because we talked about transformations of this bottle or a glass or things like that. We have also talked a little bit about how symmetry groups are useful in quantum physics. But now I want to show you how the same groups, symmetry groups, also show up in the study of numbers. So what kind of numbers I'm talking about? Well, first whole numbers, of course, 1, 2, 3, 4, 5, etc. Then you got 0, and you got negative numbers. So this is what we call whole numbers or integers. So you have this infinitely many integers. These are the first numbers we encounter. Then we want to divide things. So that brings us to the idea of rational numbers, which, of course, by the way, not called rational because they are well behaved, but that's because they are ratios. Fractions. They're ratios of two integers, like 7/31 or 9/25, etc. Okay? And for a long time, mathematicians actually thought that those were the only numbers that existed. Pythagoras thought only fractions existed, or had the right to exist. And whenever a number appeared which was not a fraction, it was not a legitimate number somehow. It needs to be sort of swept under the rug, skirted and condemned. Such as square root of 2. Very quickly you encounter square root of 2. What is the square root of 2? You can look at the square of side 1 and the diagonal on that square. The length of that diagonal will be square root of 2 by Pythagoras' theorem. So the number seems to exist. It's the distance between those 2 points, between those 2 corners in a square, right? But then very quickly you realize, it's very simple proof, to see that it cannot possibly be written as a ratio of 2 integers. Okay? So we have to, if we want to do justice to numbers, we have to throw in this number. We have to include it. Okay? So if we include, what does it mean we include it? Well, we include this number, then it kind of like opens kind of almost like a Pandora's box. You have to then allow also to multiply this number by a fraction, because we already accepted fractions. And you should also allow to add a fraction to it. So you get numbers like this, a plus b squared of 2. And this is already good because, first of all, if you have two such expressions, you can add them up, just component-wise, right? But also you can multiply the two, because when you multiply, you will get, again, numbers of the same form, but also you will get, square root of 2 multiplied by square root of 2. But when you multiply square root of 2 by itself, you get 2, just by the very definition of square root of 2. That the square root of 2 is 2, right? So you never leave, if you take these numbers, you can add them up and multiply them, and you never leave this realm. It's closed under addition and multiplication. So we get a new numerical system. And mathematicians call it a number field. We get this number field. And now here comes the main point. The main point that once you start studying this, you notice that such a numerical system has hidden symmetries. In this case, the symmetry is flipping the sign in front of square root of 2. It changes the number, obviously. I mean, if b is not, unless b is 0, then it doesn't change. But if b is non-zero, it changes the number. Say you had 1 plus square root of 2, it will go to 1 minus square root of 2, so you get a different number. In what sense is it a symmetry? It is a symmetry in the sense that when you do that, all the, it will preserve all the properties of those numbers. For example, if you take the product of two numbers before you apply this operation, or after you apply this operation, or you can apply the operation to the two numbers and then take the product, or you can take the product and apply the operation. It will be the same. And the reason why it is so is because square root of 2 and minus square root of 2 solve the same equation, because each of them is a square, each of them squared gives us 2, right? So you see, it's a very important point, because if you take minus something and you square it, the minus is gone. So here, this is an important point. You have an equation, x squared equals 2, and it has two solutions. One is the square root of 2, and the other one is negative square root of 2. So there are two solutions, which as it should be, because the equation has degree 2. So there have to be two solutions. Square root of 2, negative square root of 2. And there is a symmetry which exchanges them. And that's what we see when we consider these numerical systems. And this is a very powerful idea, which is one of the most important, I would say, one of the most important ideas of all of mathematics, which actually came to us through the work of a brilliant French mathematician, Évariste Galois. He was a genius who actually died in a duel at the age of 20. And actually, he died on May 31st, 1832. And today is May 31st, so it's a day of, not exactly around, number of years, but it happened on this day in 1832. And, the night before he was killed in a duel, he was frantically trying to finish. He knew that he was going to die, I guess, subconsciously, and he was trying to finish his papers, which, by the way, they were so revolutionary that mathematicians couldn't understand them for another 20, 30 years before, he was given his due recognition. And I always think of, I kind of always conjure up, when you study mathematics, mathematics is like a love affair to us mathematicians. And when I think about it, I always, it always brings this image of Galois, this young guy. He's writing this. What is he writing? He's not writing a love letter to his girlfriend. He's writing a love letter to all of us in some sense. He's writing this stuff because he wants to share it with us before he dies, right? And I really think that Galois groups are like the wonders of this world, really, like, Egyptian pyramids or the Hanging Gardens of Babylon. The difference is we don't have to travel through time and space to find them, to see them, to appreciate them. They're right here at our fingertips. They belong to all of us. Nobody can take away Galois groups from us, right? I mean, we may not be aware that they are out there, but they are out there and they're waiting for us to discover them. So how does it work? Galois was interested in trying to solve polynomial equations. What do I mean by polynomial equation? Well, at school we studied this equation, quadratic, which we call quadratic equation, ax squared plus bx plus c equals 0. There is a formula for it, which I'm not going to write, so as not to trigger any unpleasant memories. Important thing to know about that formula is that it involves taking the square root square root is involved somehow, right? Well, of course, for example, even for the simplest one, x squared equals 2, we have to take the square root of 2, right? But if you want to write a general formula in terms of the coefficients, you see, the coefficients are fixed, a, b, c, and x is the variable. We want to solve it for x. And we use a, b, and c as input. So you ask, what is the formula for x given a, b, c? It's a formula which involves a, b, and c, and it involves the square root. Once we understand that, and by the way, this was already in a book published in year 830 by Al-Khwarizmi, which had, in the title of the book, there was the word algebra, which gave the name to the subject, algebra, year 830. Then, of course, mathematicians were wondering, well, can we also solve a cubic equation? So they will start with x cubed. And yes, there was such a formula produced in the 16th century. And then for the quartic equation, equation of degree 4, also in terms of taking roots. But for cubic, you need cubic root. And for degree 4, you need a root of order 4. What we call radicals. Radical is either square root or cubic root or nth root. And then the question was, can we do it for the 5th? Can we do it for the 6th? And so on. And so for almost 300 years, mathematicians tried to find a formula for an equation of degree 5, just like that, in terms of its coefficients, in terms of radicals. And they couldn't. And then Galois came, and he said there is a reason why you cannot find it. It's because there is no such formula. So you see there is a fundamental difference between equations of degree 2, 3, and 4 and the equation of degree 5 and higher. And the way he explained it is by using what we now call Galois groups, by using groups. He said, let's not try to solve it. Let's not try to find a formula for the solution. Instead, let's look at the symmetries. It's almost like, the French say, cherchez la femme, And Galois said, cherchez le groupe, search for the group. Search for the symmetries. That's where you will find it. That's where you will find the answer. We can look at the symmetries and we can discern the structure of solutions by even not knowing what the solutions are, if we can understand their symmetries. Here's how it works. The simplest way Galois group works is going back to our square root of 2. Remember, there are two solutions of the equation x squared equals 2. Square root of 2, negative square root of 2. We can exchange them. It is like exchanging the two wings of a butterfly. A butterfly is symmetrical. Why? Because we can exchange the two wings and it will stay the same. Likewise, we can exchange the two roots of the equation x squared equals 2. It will stay the same. So this butterfly group of two elements, exchanging or not exchanging the two elements, is the Galois group of the equation x squared equals 2. It has very simple structure. And here's what it will look like for an equation of degree 5. A general equation of degree 5 will have 5 different solutions. We don't know what they are. We would like to write a formula, but we don't know what they are. It's okay. Let's just represent them by these little circles. A symmetry, then, of the equation would be a permutation of these 5 solutions. The way one of the permutations is written here, but there will be many others. The first one will go to one of the 5. The second one will go to one of the remaining 4. The third one will go to one of the remaining 3, and so on. That will be a permutation. If you have 2 such permutations, you can apply them back to back. You'll get a new permutation. That's why it will be a group, for the same reason that rotations of a bottle form a group. And now the point is that this group that for a general equation, the symmetries of the solutions will comprise all possible permutations. There will be 120 of them, 5 factorial. 1 times 2, because first time you choose 5, then you choose 4, then you choose 3, then you choose 2, then you choose 1. There's no choice. So 5 times 4 times 3 times 2, if I calculate it correctly, is 120. Which, by the way, this group, interestingly enough, is almost the group of all symmetries of icosahedron. The 5th element that Robert was talking about, Platonic solids. And the most complicated Platonic solid is icosahedron, which has these triangles. There are 5 edges emanating from each vertex. Its group of symmetries is almost the same as this group. It's up to a factor of 2. So it's very interesting that the same group actually shows up in geometry as well. But Galois' point was that this Galois group of symmetries of the quintic meaning equation of degree 5 has a much more complicated structure. Not just because it has 120 elements, but just because we can look at its structure. It has a much more complicated structure than the groups that show up for polynomials or for equations degree 2, 3, and 4. And its structure is such that it prevents us from finding a solution in terms of radicals. So I don't want to get too technical, but it's basically the idea is that you can only find a formula in terms of radicals if the group has a certain simple structure. And from degree 5 and higher, it just doesn't. That's why there is no formula. That was his solution. So what I want to say is Galois did not solve the problem the way it was understood. The way it was understood is, let's just find a formula. We found it for quadratic and cubic and quartic. Why can't we find it for quintic? But he kind of hacked the problem. He looked at it in a different way. He said, let's look at symmetries. And this way, he found out why the original problem was not, posed in the right way. Now I want to talk a little bit about symmetry of harmonic analysis. Remember, circling back to the idea of unification. We want unification in mathematics. There are different areas of mathematics, different subjects in mathematics. We talked about number theory, we talked about geometry. Now I want to talk about harmonic analysis, another continent in the world of mathematics, which has to do with harmonics, with the sound waves. And the simplest sound waves are sine and cosine functions, right? We can draw them like this. What is special about the sine and cosine? It's again, there is some property with respect to a group of symmetries. A sine and a cosine is a periodic function. Each of them is a periodic function. If you shift the argument by 2 pi, which of course 2 pi is a euphemism for 360 degrees, right? If you shift by 2 pi, it stays the same. Likewise, it's the same for sine and cosine. But what does it mean? What if I shift by 4 pi? It will still be the same, because shifting by 4 pi is the same as shifting by 2 pi and shifting again by 2 pi. Each time it will not change, so 4 pi will not change either. 6 pi will not change. Negative 2 pi will not change. There's a whole group of symmetries of the line which acts by translation, by shifts, by multiples of 2 pi, by 2 pi, 4 pi, 6 pi, and so on. And this group is these two functions are invariant under this group. Invariant means doesn't change under these transformations. That's what's so special about sine and cosine function. And actually more general functions, sine of multiple of x or cosine of multiple of x, where the multiple is an integer itself. So geometrically, you can think about it like this. There's a typo in this picture, though. It should be 0, 2 pi, 4 pi, negative 2 pi, negative 4 pi. But that's the idea, that there are shifts. There is this, the function is defined, sine or cosine, is defined on the entire real line. But we only need to know it on one of the intervals, because then we will know what it is on the other intervals by shifting, right? Because the function doesn't change under the shifts, and therefore, if we know it from 0 to 2 pi, say, we'll know it from 2 pi to 4 pi. That's how it works. But more generally, so we can sort of take this idea and run with it, and consider more general spaces, not necessarily a real line, and more general symmetries, not necessarily translations like this. And we can study the basic harmonics, which would be the functions invariant under such transformations. And a great example of this happens when the space is a unit disk. There's a unit disk on the plane. A unit disk on the plane. The group which acts also has a fancy name, but now we are used to these names. We already talked about SO3 and SU3 and so on, SO10. So this is SL2Z. Z stands for the integers and a special linear group. It can be realized by 2 by 2 matrices whose entries are integers, and the determinant is 1. It doesn't matter. This is a technical issue. There is a certain group. What I've drawn here is how it acts. These triangles, you see these triangles that we have here, kind of curved triangles, they are the analogs of those little intervals which were on the previous picture. Here. Here, what played the role of an interval here is now played by by one of those triangles. So the functions, the harmonics in this world will be functions which are determined by their values, and there are infinitely many of them. They're kind of becoming smaller and smaller. It's really a beautiful picture. And so these harmonics are called modular forms. So this is a very important example from harmonic analysis. So modular forms are like a sine function or cosine functions. It's the same idea, except we're now in a more sophisticated space, namely a unit disk rather than on a line. And so now we come to the crux of the matter, the Langlands program. Langlands' idea was that the two continents of mathematics, number theory, which we talked about earlier, things related to solving polynomial equations and Galois groups, and harmonic analysis, the other continent, things related to, decomposing the sound of a symphony into harmonics, or more general functions into harmonics on more general spaces. That these two worlds, these two continents are actually connected. There are hidden connections between them, hidden and unexpected connections. So it is like finding order in a seeming chaos. You get a problem in number theory, which typical problem in number theory would involve counting numbers of solutions of some equations. You can solve them on a computer in some small cases, and you generate a sequence of numbers. And they seem to be completely random and chaotic. But Langlands was able to reformulate that question in the language of harmonic analysis. And in the language of harmonic analysis, we could actually, one harmonic function, one modular form, one harmonic, can have the answer to all of those in one stroke. So it's almost like, I like to think of it as sort of like a source code. You're finding a source code of some intractable mathematical problems. So what's an example of this? Well, there's one example which pertains specifically to modular forms, which we just talked about. Remember that disk with those little curved triangles on it. And in this particular case, this Langlands statement, this Langlands correspondence between these two continents has been proved. And in fact, this is what led to the proof of Fermat's last theorem. Fermat's last theorem, of course, one of the most famous problems in all of mathematics. Pierre Fermat, a great French mathematician, realized that if you take, equation x to the n plus y to the n equals z to the n has no solutions x, y, z in whole numbers if n is greater than 2. And he wrote about it on the margin of a book he was reading. It was actually Diophantus arithmetic. And he said, I found a marvelous proof of the statement, but this margin is too small to contain it. Which I kind of like to think as a 17th century Twitter-like proof, It's like, I have this beautiful idea, but 140 characters, it's not enough to express. So the search was on for a proof, and for 350 years almost, actually more than 350 years, we did not have a proof until Andrew Wiles and Richard Taylor gave one. But it was based on a realization earlier by my colleague at UC Berkeley, Ken Ribet, in 1986, that actually Fermat's last theorem followed from that special case of the Langlands program that involves modular forms. So this is a big deal. It led to the solution of one of the biggest problems of all of mathematics, the Fermat's last theorem. But, it's only the tip of the iceberg. There are many, many statements like this which are still unproved, for which we still don't know the proof. And we still don't understand why. Even in the case which was used to prove Fermat's last theorem, which involves modular forms and Galois groups, which was proved by Andrew Wiles and Richard Taylor. Even in this case, I would say we still don't understand why. We can convince ourselves the math works out, but I still think that the jury is still out as to why this should be true, why these connections exist. They point to something really mysterious, kind of still beneath the surface. And that's why so many mathematicians find these ideas so fascinating. What's also interesting is that initially Langlands was really concerned about connecting number theory and harmonic analysis and obtaining some deep insights about both fields using these connections. But in fact, these ideas have since, we're talking about, since late 60s, that's when Langlands first came up with these ideas. These ideas have propagated now to other areas of math and physics, to geometry in particular, and even to quantum physics. And this is something which, some recent work, which I have been involved with some wonderful physicists like Ed Whitten at the Institute for Advanced Study in Princeton. And I won't tell you all the details about that, but I just want to mention that the connection to physics goes through what's called electromagnetic duality, which is a fascinating concept, which actually is something that we can observe by studying electric and magnetic fields using Maxwell's equations. So James Clerk Maxwell wrote this very beautiful, very elegant system of equations governing electric and magnetic fields in the second half of the 19th century. And electric field, we come to get to know electric field and magnetic field in very different ways, right? I mean, electric field is something responsible for the lightning, for example, and magnetic field is something that gives our, the compass, orients the compass in the right way. But it turns out that if you look at the equations and you exchange electric and magnetic fields in the equations, in Maxwell's equations, the equations will stay the same. Well, in vacuum, strictly speaking, in vacuum, but it's a very surprising property of the equations themselves. And so it's something you cannot really see if you just kind of go out and study, nature. And you would be seeing electric, you would be seeing magnetic, but it would be very difficult to see that the two are connected. It's only when you write the mathematical equations governing these forces that you can come to this realization. And this is somehow a very important element, I think, which is lost even on some scientists sometimes, which is, I think there is this sort of prevailing sort of impression of mathematics playing sort of a secondary role in science, that scientists get some data and mathematicians are trying to feed that data into some mathematical models. But that's not always the case. Sometimes that, of course, is one of the important modes of operation. But we talked earlier about how Riemann discovered his Riemannian geometry without having any specific applications in mind, and yet it was very useful for Einstein's relativity theory, or about Gell-Mann talking, using SU3 for understanding elementary particles. And this is another example. We see electromagnetic duality by looking at the equations. So you have to first write down the equations which govern electric and magnetic forces to be able to come up with this insight. And so there's a beautiful story, continuation of the story, when we go from the sort of classical world of classical physics, low energies, large distances, to the world of quantum physics, high energy, small distances. And it turns out that physicists have theorized that something like electromagnetic duality might also be happening at the quantum level. And it is this quantum electromagnetic duality and its generalization in supersymmetry. So all the things that Robert Dijkgraaf talked about in the previous talk about supersymmetric generalizations of quantum theories, gauge theories, and so on. So when you look at this sophisticated quantum field theories, physicists theorized that they exhibit a sort of electromagnetic duality. And it was discovered in the last 10 years that that electromagnetic duality is intimately connected to the Langlands correspondence, to the kind of links and unexpected connections that we came to know through the work of Langlands. So there's a book that I wrote recently, it's called Love and Math, in which I talk about the Langlands program, and I give much more detail, you can find much more details about this, in particular, about this connection to electromagnetic duality. But if there's only one image I want you to stay in your mind after this talk, is this. A giant jigsaw puzzle. We're trying to solve this jigsaw puzzle, and there are different continents that we're trying to connect. And then connecting it to physical reality, to the physical world. Because, as Charles Darwin very aptly said, he did not like mathematics when he was a student. Surprise, surprise. It's true for most of us, I guess. It was certainly true for me. But then later in life, he came to realize that mathematics was important, and he said, I deeply regretted that I did not proceed far enough, at least to understand something of the great leading principles of mathematics. For man, thus endowed, seemed to have an extra sense. And I'm not trying to imply that, we mathematicians, we have this extra sense, so that's somehow very important. Because the point is that all of us have this extra sense. just like we have other senses. It's just for some of us, it's less developed than for others, but there is nothing to stop us from developing that sense and from connecting to these wonders of the world, which come from the world of mathematics. And it's really, I think, important point here also is that most of the things are still unsolved. We have, made tremendous progress, and we know many things. But the more we know, the more we know how little we know, right? And so each time, each solution, each problem, when it's solved, allows us to push the veil over the unknown, and we realize some problems which you didn't even know exist. And it's almost like Newton said, it's almost like we are like children playing on the seashore and diverting ourselves now and then, finding smoother pebble or prettier shell, whilst the great ocean of truth lay all undiscovered before us. So I say, let's go out and find more of those truths. Thank you very much.